And if we could observe the universe in its most remote past, we would witness a spectacle that defies all imagination. A cosmic carousel in which two entire galaxies approach each other at insane speeds, wrapped in a whirlwind of incandescent gas, dying stars, and a blinding light gushing from an infinitely small yet powerful point. This is the heart of chaos, a quasar, one of the brightest and most violent objects ever conceived by physics. It is not merely an astronomical event, it is a moment of creative destruction, a collapse that shapes the very structures of the universe. And all this happened 11 billion years ago, when the Milky Way was still a child and the light from those galaxies began its journey to reach our telescopes. Thanks to the synergistic combination of the ALMA and VLT telescopes, two of the most advanced optical instruments ever built, astronomers were able to observe this colossal event as if leafing through the opening pages of a cosmic book. The object in question is at such a distance that its light has taken most of the history of the universe to reach us. It is a case of two colliding galaxies that host, at their shared center, an active quasar. This halo of extraordinary energy is nothing but a source fueled by a supermassive black hole devouring matter at a frantic pace, transforming gas and dust into electromagnetic radiation that shines brighter than 1,000 billion suns combined. But it is not just the visual spectacle that makes this observation unique. What surprised scientists is the devastating effect of the quasar on star formation. Normally, when two galaxies collide, the gravitational chaos triggers a frantic flurry of star birth. Gas clouds compress and give rise to thousands of new stars. In this case, however, something radically different is happening. The quasar, instead of fostering the birth of stars, is halting it. High-energy radiation outflows are literally sweeping away the cold gas necessary for star formation. It is as if the universe were sabotaging its own creative mechanism. This phenomenon is known as quasar feedback, and it is one of the key ingredients for understanding the large-scale evolution of galaxies. Essentially, when a black hole at the center of a galaxy grows too quickly, its energy can heat or expel interstellar gas, preventing further episodes of star formation. It is a process of cosmic self-regulation that stops galaxies from becoming too large, too quickly. In this scenario, the quasar acts as a fierce guardian, controlling the growth of its realm of stars, maintaining a delicate and dynamic balance between destruction and creation. But what makes this discovery so extraordinary compared to other galactic collisions? The fact that it occurs in such a primitive epoch of the universe, when galaxies were still in their early evolutionary stages, offers us a unique window onto the genesis of cosmic structures. Observing such a powerful quasar in such an ancient context means that supermassive black holes must have formed and grown at a staggering pace, calling into question many well-established theories about the origin of these dark giants. Some theoretical models suggested that black holes grew slowly, absorbing matter over billions of years. But events like this force scientists to radically revise their timelines. It is possible that still unknown mechanisms allow a black hole to reach masses greater than 1 billion times that of the Sun in less than 1 billion years. Perhaps through the direct collapse of extremely dense gas clouds, or through multiple mergers in hyperdense environments. Or, and here speculation becomes bold, through phenomena related to dark matter or quantum vacuum physics, which could accelerate black hole growth in ways yet to be understood. All this brings with it an inevitable question. How much of what we observe today has been shaped by similar events, invisible but omnipresent throughout the history of the universe? Our own galaxy, the Milky Way, has likely gone through similar tumultuous phases, hidden in the depths of time. The signs are there, in the movements of the oldest stars, in the distribution of dark matter, in the remains of cannibalized galaxies visible only through the most refined spectroscopic analyses. And as we continue to scan the sky in search of new evidence, this primordial collision becomes much more than a mere observational datum. It becomes a key. A key to understanding how galaxies transform, how energy is distributed in the cosmos, and above all, how the most destructive forces of the universe can, paradoxically, be the true architects of its complexity. If we consider that the light from that event took over 11 billion years to reach us, we realize we are observing a fragment of the cosmos history so remote that it brushes the very limits of observability. It is as if the universe, in an act of quantum nostalgia, were sending us an echo of its most violent and formative childhood. But what is even more fascinating is that events like this are by no means rare in the young universe. They are actually quite common, and may have been the main drivers of large-scale cosmic restructuring. Most of the galaxies we now see as stable and well-defined entities billions of years ago, have been the result of cosmic mergers and hyperactive quasars. Yet, as advanced as our instruments are, we cannot see everything. Current telescopes, powerful as they are still blind to many of the frequencies and details of these events. And this is where future missions come into play. The James Webb Space Telescope, already operational, is revolutionizing the way we see the cosmic past, but it will not be alone. New instruments like the Nancy Grace Roman Space Telescope, coming in the next few years, or the Vera C. Rubin Observatory, with its ability to map entire portions of the sky each night, promise to turn these exceptions into rules, bringing to light hundreds, perhaps thousands of galactic collisions with quasars in action. The implications are immense for another reason as well. These collisions appear to alter the distribution of dark matter. Although invisible, dark matter exerts a fundamental gravitational force in the formation of cosmic structures. Some studies suggest that interactions between galaxies, especially those fueled by quasars, can reshuffle dark matter, creating vortices and concentrations that modify stellar orbits and even the structure of galactic arms. In practice, we are not just witnessing a dance of stars. We are seeing how the very map of gravity in the universe is redrawn. And then there is the most evocative aspect, the connection to life. Every star born, every collapsing gas cloud, is potentially a cradle for new planetary systems. Halting star formation in an entire galaxy, as the quasar in question does, means preventing the birth of billions of worlds, and with them, perhaps, the possibility of life. It is a dizzying reflection. The energy unleashed by a black hole could decide the biological destiny of entire regions of the universe. And if this is true, then our very existence might be the result of a fortunate cosmic truce, a precarious balance between destruction and creation that allowed our sun to form in a moment of peace. It is no coincidence that cosmology today is moving ever closer to a philosophical dimension. Physics provides us with the tools to measure, calculate, predict. But events like this force us to ask deeper questions. Why does the universe have this structure? Is it the result of chance, of inevitable laws, or of finely tuned initial conditions? And if there are other universes with different laws, what happens to the galaxies in those worlds? Are there quasars that do not destroy, but generate? Galaxies that evolve without ever merging, or that live in eternal equilibrium? To these questions, for now, we can only respond with imagination and relentless research. But every new observation, every newly documented galactic collision, brings us a little closer to understanding the grand design. In the meantime, the light from that ancient quasar continues its journey, crossing cosmic darkness like an encrypted message, destined for eyes able to read it not only with optical instruments, but with a deep desire to understand where we come from, and where we are going. And perhaps this is the secret power of such distant and yet so powerful events. They remind us that the universe is in constant motion, that nothing is static, and that even in the most total destruction may lie the beginning of something new. A star, a world, a possibility. If you have made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.